Tutorial 3, question 2. Two reactions occur in a process, which is this two. The feed is 85 mole percent of ethane, C2H6, with the balance being inerts. The fraction conversion of the ethane is 0.501. So this is specification number 1. And the yield, which is the ratio of the moles, of the number of moles of C2H4 produced to the number of moles of C2H6 in the feed, which is 0.471. Calculate the composition of the product using A, element balance, and B is species balance. So here's the process. We have our feed, and over here we are taking a basis of 100 mole, and it says that the feed contains 85 mole percent of ethane. This one is a mole fraction, yeah. 0.85 of C2H6 in the feed, and 0.15 of them are inerts. In the product stream, because we do not know whether if C2H6 will be completely reacted, so we have to put that there is C2H6 coming out. Okay, and since inerts are non-reactive, therefore you should also have inerts coming out from the product stream. And then over here you also have C2H4, CH4, and H2. For part A, elemental balance. So using the specification number 1, the fraction of conversion of ethane is 0.501, which means the number of moles of C2H6 that is remain, so that there is a 0.501 fraction of ethane is converted. Therefore, the remaining one comes out, right? So we take 1 minus this one, which is the remaining part, multiply by the feed of number of mole of ethane in the feed. So that is 1 minus 0.501 multiplied by 0.85, which is the composition. The composition over here times the feed, and our feed is 100 mole, which will give us 42.415 mole of C2H6 coming out in the product stream. Moving on, we have specification number 2, and that actually means the number of moles of C2H4 coming out over the number of moles of C2H6 going into the feed stream, and this ratio here is 0.471. So we can easily calculate the number of C2H4 coming out, because we already have this info here, and therefore we will get 40 moles. To do element material balance, or element balance for the inerts, since inert is not reactive, therefore whatever inert goes in should come out. So the number of inerts coming out is the number of inerts coming in, which is 0.15 multiplied by the feed, and you get 15 moles of inert in the product stream. Let's write this down back over here. So we found that C2H6 coming out is 42.415, and the number of inerts coming out is 15, and you have over here 40 moles. So all we are left is the number of moles of CH4 and H2. We will then proceed to performing element balance using the element C. So element balance, basically we look at each single element in one component. For example, you may have CO2, so the element inside is C and O. So for element balance, in is still equal to out, so the number of moles of C2H6 going in. So the component in the feed that has C, the components that has C is C2H6. This one is in it, right? So we have number of moles of C2H6 going in. So C2H6, we have 2 moles of carbon. 2 moles of carbon in 1 mole of C2H6 equals to the number of C2H6 coming out. So C2H6, you have 2 moles of carbon per mole of C2H6 plus, what else you have coming out? The ones that comes out in the product stream that contains carbon. Okay, the next one is CH4. Okay, we also have C2H4 over here. So CH4, you only have 1 C, 1 mole of C per mole of CH4, plus another one, C2H4, you have 2 moles of C per mole of C2H4. 2 moles of C per mole of C2H4. So this one we already know. Sorry. We know that the number of C2H6 going in, this one is 85, which is 0.85 multiplied by 100. Okay. C2H6 coming out, we already have it. This is 42.215, and we don't know this, but we know C2H4 coming out is 40. Then you can easily solve for the number of moles of CH4. So the number of moles of CH4 coming out in the product stream is 5.1 mole. Put this in, 0.1 mole. Now you have H here, right? So the next component balance that you have to do is H, the element H. Same thing here. What goes in is C2H6. This component here, this guy here, has hydrogen, right? So the number of C2H6 going in. So C2H6, you have 6 moles of hydrogen inside 1 mole of C2H6. So you multiply by 6. And whatever comes out with H element inside, you sum it up. So we have number of moles of C2H6, so you have 6 here. Number of moles of C2H4, so you have 4 moles of H per mole of C2H4. The number of moles of CH4 coming out, and you have 4 moles of H per mole of CH4. Finally, you have the number of moles of H2 coming out, and of course you have 2 moles of H here per mole of H2. So this one over here, this is 0.85 again times 100 will give you 85. C2H6 here is 42.215. This guy here is 40. CH4 we have found previously from C element balance. You get 5.1. So all you're left with this. And we found that the number of hydrogen coming out is 37.485. And the question actually wants you to calculate the composition of the product, so meaning to say you have to calculate it by percent. To calculate it by percent, so basically this part here is you have to have number of moles of C2H6 over the total number of moles of the product multiplied by 100. So to find the product, we'll need to sum up all the components in the product stream, okay, which will give us a value of 140.035 moles. So we have filled in here. Now for example over here, C2H6 is 42.215. Over here this one is 42.215 over 140 times 100, which will give us about 30.3%. Okay, you may do the same for the following. For part B, we are going to do species material balance. So species material balance, we will use the extent of reaction in the stoichiometric ratio. And we will do the balance in terms of each component itself instead of taking the element, for example, C, H, O, like that. We will not do that. We will take C2H4 as a whole, the compound as a whole, to do the material balance. Let's start. So the first one over here is specification 1. So we will use 0.501, which is the conversion of ethane, multiplied by the number of moles. So this over here is the number of moles of C2H6. Okay. And the value here is actually 42.6 moles reacting. So what does this mean? If we look at the equation again, C2H6 is involved in two parallel reactions, because the C2H6 that is remain over here may react with the hydrogen over here to form CH4. Therefore, for reaction 1, we will have one extent of reaction. Reaction 2, you have extent of reaction number 2. Each reaction will be based on its extent of reaction, because each reaction is different. So this is an overall. This is based for the conversion here is for the overall C2H6 here. Therefore, this 42.6 mole reacting is actually a combination of extent of reaction 1 plus extent of reaction 2. Next, specification 2 is the same as the one before. So you have what it is here. This one is same, which is same as part A, where you can find the number of moles of C2H4 coming out. Is this. So C2H6 going in this is 85. Then you will get 40.035 mole. So we can take the extent of reaction 1. The equation for it is the number of C2H4 coming out, okay, the number of moles of that component coming out, minus the number of moles of C2H4 going in. Why are we taking the extent of reaction number 1 is because we already have the value of number of moles of C2H4 coming out. So if we look at the reaction equation here, C2H4 is involved in reaction number 1, but you don't have C2H4 in reaction number 2. That is why, since we already have this information given, we also have this, might as well we use the extent of reaction for the first reaction. So the number of C2H4 coming out is what we found, and there's nothing coming in. Okay, there's no C2H4 going into the reaction. If you look closely, it's only C2H6 based on equation 1, yeah, reaction 1. And the stoichiometric ratio is 1, and we found that extent of reaction for number 1 is 40. And we can easily find extent of reaction 2, since we already know this is 2.6. So based on the general material balance equation, we know that the number of moles of the component going in minus the number of moles of component going out plus the generated species as well as the consumed species is equal to 0. And this part here, the generation and consumption, because this part here only happens when there is a reaction. So how do you represent it with a reaction? You can represent it using the extent of reaction multiplied by its stoichiometric ratio. This is the same, this part here is the same as like this. N out minus N in over 3. Okay, so bring this over. Okay, but this one is based on the reaction. So we can simplify it further. So the number of moles of that species coming out is equal to the number of moles of that species going in plus the sum of the extent of reaction multiplied by its stoichiometric ratio for each species. So let's do this one. The number of moles of C2H6 coming out. So you have the number of moles of, let me show you. The number of moles of C2H6 coming in is 0.85 times 100. Okay, plus extent of reaction 1 multiplied by the stoichiometric ratio of C2H6 for reaction 1 plus extent of reaction 2 multiplied by its stoichiometric ratio for reaction 2, 6, which gives us 85 plus we have to check back the reaction itself. So extent of reaction 1 is 40 multiplied by V1. V1 over here, so this is -1 plus extent of reaction 2, and that one would be 2.6, also -1, which will give us a value of 42.4 moles. You may do the same for the following, which is to find the number of moles of C2H4 coming out. Number of moles of H2 coming out. Number of moles of inerts coming out. And then, did I mess up? Yes, number of CH4 coming out. And find its total, which is P.